In the past, dynamics has usually been introduced late in a school course, with an algebraic approach, with a few demonstration experiments, and strict definitions of terms such as force. Very often, when the algebra was forgotten, little else remained. I hope to show how we can gradually build the concepts involved in a study of force and motion, starting at an early stage with a qualitative feel for the terms, and later adding a more quantitative approach with modern techniques once the algebra has been acquired. Early in the course, the pupils will experience for themselves various kinds of forces as a series of pushes and pulls. For example, stretching rubber, pulls with springs, twisting forces, magnetic forces, electric forces, the pull of gravity. The forces demonstration box can help to give young pupils the feel of various forces. They can be left in the laboratory over a period. They can gain acquaintance with the feel of a pound weight, a kilogram weight, and a newton. But it's a question of the feel of the forces, no definitions at this stage. Having introduced the ideas of force, the time comes when we must instill confidence in the concepts of velocity and acceleration. This requires lots of pupil experiments in the laboratory. It also involves the measurement of time, and here the ticker tape vibrator is essential. This device comes in various forms, which operate from a low voltage AC supply. In this timer, the vibrating strip of metal has a frequency of 50 cycles per second. The paper has been threaded, the point hits the rotating carbon disc, and when the paper is pulled through, it is marked with a series of dots. A good introduction is to allow the pupils to move away from the timer. Let them walk, run, slow down, and stop. If we let them swing their arm, an interesting record is obtained. The tape should be cut up into lengths corresponding to the same time interval. Say 10 ticks. Instead of rushing into a formal treatment of graphs, tape charts should be constructed. I have one here. The pupils should relate the various parts of the chart to the motion. This can lead to an investigation of free fall. We have the timer set up like this, with a weight attached to the tape. We switch on the vibrator and we release the tape. Diluted gravity can be investigated using these trolleys on this type of runway, which can be inclined like this. I switch on, and produce a tape which can be cut up to produce a chart like this one I've already made. Diluted gravity leads us at this stage to Galileo's incline experiments. Supposing we start a ball here, what will happen on the other side? Now, supposing we reduce the upslope, like this. What will happen in this case? Starting from the same height, the pupils tell us that it reached the same vertical height on the other side. Now, suppose I reduce this upslope even more, like this. What will happen to the ball in this case? And in the limit, when this side is laid flat, this will produce the idea that the ball should go on forever. But in fact, it doesn't. And here we come to consideration of friction. Some experiments on friction as a force are appropriate here, but instead, in this film, I'll concentrate on reduction of friction. Polystyrene beads can help us here. And at this point, the concept of inertia can also be introduced. The pupils should get the feel of the inertia of a pound of stuff or of a kilogram of stuff. A useful device for reducing friction involves the hovercraft principle. I have here a large glass plate which has been carefully cleaned all over using meth and polished like this. I need to level carefully using these rubber wedges. On the plate, I place this magnetic ring puck, underneath which I'm going to put some solid CO2. I can obtain this from the gas cylinder. The gas is now coming out from underneath so that the puck is riding on a frictionless cushion. In this way I can encourage the ideas of Newton 1, motion without force. And again, by increasing the mass, the concept of inertia can be encouraged in this way. We have a technique of stroboscopic photography for use later in the school course. A simple camera is placed above the plate on this gantry, and a motor-driven stroboscope, which I'll switch on now, placed in front of the camera. With sufficient illumination for a puck, we can take a photograph. A daylight loading tank can be used to develop the picture, and details are given in the notes accompanying this film. Alternatively, instead of using the motor-driven stroboscope, a xenon flasher can be used. Can I have the lights down, please? This photograph was taken in that way. You can see equal distances travelled in equal intervals of time. You will see more of these techniques in the film Momentum and Collision Processes. Our study of motion should include motion in 2 dimensions. Let the pupils start by dropping 2 equal masses simultaneously. Then ask them, what happens when one ball is given an initial horizontal motion? How will this affect the time of fall? Let the pupils investigate this for themselves. Here is an elegant little device. I have 2 spheres here, and when I release the catch, these are released simultaneously but this one is given an initial horizontal motion. Let's try it. A particularly beautiful demonstration of projectile motion is the pulsed water drops experiment. This tube is connected to a constant head of water, but on the way passes through a vibrator fed from the AC supply, so that from this jet passes a succession of droplets of water. Here we have a compact light source, and the light is focused by this lens onto the strobe disc, which is rotated by this motor. So here we have pulsed water droplets illuminated by chopped light. So on the screen will be projected an enlarged shadow of the drops, apparently motionless. The screen is translucent so that the pupils can view from the other side when they will see this picture. Lights, please. This lends itself to a quantitative analysis of the independence of the vertical and horizontal motions. Alternatively, we can illuminate the droplets using the xenon flasher and view them directly. In that case, of course, lots of this apparatus is really unnecessary. So, let's have it removed. What a lab assistant. Lights off, please. Now you can see why we call this experiment perils in air. So far we have discussed forces and we have discussed motion. Now we must relate them together. So let's return to the trolleys and runway. The work on friction will suggest the need to friction compensate to provide a uniform velocity once the trolleys are set in motion. We can ask the pupils how to check that it was a uniform velocity. We can apply a force to the trolley using this length of elastic. Attach the ticker tape using the sellotape. Stretch the elastic between the pillars, and once we've switched on the vibrator, we can let it go. With a little practice, the pupils will soon apply a steady pull. Cut up the tape in the usual way and make a chart. Then double the force using 2 elastics. Then with 3 elastics. Here are charts obtained in this way. 1 unit of force, double the force, treble the force. The increase in acceleration is quite obvious. Now, compare 1 trolley pulled by 1 cord with 2 trolleys, again pulled by 1 cord. We may need to recompensate for friction. And we can have 3 trolleys pulled by 1 cord. The concept of inertial mass has therefore been taken a stage further, and we are now ready to consider momentum and energy. These are dealt with in another film in this series, Momentum and Collision Processes. What I have tried to do is to suggest a wide variety of experiments and discussion points for the pupil, each concept being given a more precise and profound significance at succeeding stages of the school course. In this way, we hope to instill a sound understanding of the physics of force and motion.